Hey everybody, Rob here from Get Some Systems. This is our first embedded video where we discuss the embedded code and our MSP430 for this toaster project. And this is going to be pretty quick. I won't be able to go into too much detail. As I said, this is a little complicated and it takes quite a bit of time to make these. So if you got any questions, look into some more fundamental tutorials I put up, or contact me, send me a message, send me an email, post. So the first thing in here is we include the MSP430G2553 header file, which is really important. If you don't know where that is, it's in your Code Composer Studio main directory. And so for me, it's in C, TI, Code Composer Base, MSP430, include, and if you scroll down, there's the 2553 header file. If you open that up, this holds all the definitions for all the keywords we use to address registers. Very important. And under that is a little functions header file that just holds some basic functions. We won't go over those. They're pretty straightforward. And all of these global variables are counters and flags that we use in our interrupt routines, and we'll wait to discuss any of these while we're going through the routine so it makes a little more sense. The first thing we do is stop our watchdog timer, and when you do that by writing to watchdog control, put the watchdog timer in hold, and you've got to add the password on there, because if you don't write in the correct value to the password, it won't shut the watchdog timer off. Next, we configure our clock to the default 8 megahertz. And I just picked this because it was simple and it's in the header file. It's actually right here in this header file. There's defined 16, 12, 8, and 1 megahertz. And so for the DCO, the digital controlled oscillator in this chip, I just picked 8 megahertz. That's plenty for me. And so the DCO sources both our main clock and our sub-main clock. And our main clock isn't divided by anything, so our main clock runs at 8 megahertz. It's divided by 1. And so it's the value of the DCO. Our sub-main clock is broken down a little bit. We divide that by 8 with the division bits here, and that puts our sub-main clock at 1 megahertz, because our sub-main clock feeds our peripherals in the chip, and we really don't need 8 megahertz, and we really don't even need 1 megahertz probably. But so I wanted to break that down so our counters and our service routines for our interrupts are a little smaller. Next, I just configured the red LED on the launch pad to be an output, so I can use that as kind of a visual indication of what's going on in my code. So timers A0, this is the first real useful kind of big section, and we use the timer A0 for 3 different things, and its associated capture compare register. CCR0 controls the temperature, power updates, and updates for the PWM value. And so that interrupts, we execute the code in CCR0 every so often, and that code controls the duty cycle and temperature monitoring. CCR1 sends the temperature data, it interrupts, executes the code, sends the temperature data to the GUI, the Python GUI, to be plotted. So this only sends, CCR1 only interrupts and sends the data to be plotted on the graph. CCR2 sends the data to the Python GUI to update room temperature and thermocouple temperatures. So that's the display on the main GUI application where we get our real-time updates. That's done by capture compare register 2. And the configuration is pretty simple. We set up timer A to use the sub-main clock as its timer clock. We divide that by 8 because we really don't need a super fast clock here. So we divide a megahertz by 8 and we get 125 kilohertz. And then we set the timer in up mode. And so up mode, we'll look at the data sheet real quick. And the way up mode works is that the timer only counts up to capture compare register 0 and then resets, and then counts up to CCR 0 and then resets, and it does that over and over and over. So the tar only gets up to the value in CCR 0 and then resets, so it doesn't count up to FFFF and roll over, and we don't use the interrupt for rolling over. So that we do that. I did that mainly because it's pretty simple, and I wanted my capture compare register to kind of be the interrupt, to be the main interrupt, because it drives our temperature and our duty cycle. And so we enable timer up mode, set up our clock to be a little lower than a megahertz by dividing it by 8. And so now we can configure CCR0, and this is pretty simple. All you do is enable the interrupt, clear the interrupt flag, and set the capture compare register to a value you want. And so for us, we want to interrupt, let's see, CCR0 interrupts 50 times per second. So if you calculate that out real quick, just use Windows calculator, take 125,000, so our clock frequency, and we want that to interrupt 50 times a second. So you divide it by 50, you get 2,500. So you just put 2,500 in your capture compare register, and it'll count up to 2,500, interrupt, execute the code, reset, count up, interrupt, execute the code over and over and over. And so that's it. Next, CCR1, we want to interrupt 2 times a second. So we take 125,000, divide it in half, we get 62,500. So that's the value we want to count up to. And again, we just enable interrupts, clear the interrupt flag, set our capture compare register to a value that will give us the right time increments, and then we'll move on to CCR2. Same thing, enable interrupts, clear the interrupt flag, and we want to interrupt 5 times a second, and 125,000 divided by 5 gives us a count of 25,000, and that's it for timer A0. Timer A1 is a little different, and it helps if you have an oscilloscope, and this is where we create our pulse width modulation. So the first thing that we do is set up our clock. So timer A is going to use our sub-main clock, divide that by 8 again, so that gives us 125 kilohertz for timer A1. Configure timer as up mode, so it counts up to CCR0, and then we use CCR0 to set our frequency. So we interrupt 5 times a second, count up to 25,000. So calculate that out. 125,000. Divide that by, and if you divide that by 25,000, you get 5. So 5 hertz, 5 times a second. And so that's going to be our frequency, 5 hertz, and CCR1 is going to determine our duty cycle. And so it makes a little more sense if we go to the data sheet for this one. They've got some pretty good charts in here to kind of point this out. So here we're in up mode, counting to CCR0, and CCR1 is going to determine our duty cycle. I guess one thing to point out, we configure the timer in toggle set mode by using the out mode _6 directive, and so that puts us in output mode 6 toggle set. So what's going to happen is we start counting, and our output on our output pin is going to be set until we reach capture compare register 1, and then it's going to reset or toggle. And then when our count expires, or our tar register for the timer hits CCR0, we're going to reset. This pin's going to go high again, and we're going to wait till we hit CCR1, and then it's going to go low. And so doing this, we can control the width right here, which is our duty cycle. We control the width of this pulse. And so the bigger the value in CCR1, the higher, the closer to CCR0 you get. So CCR0 is a limit. You can't set capture compare register 1 to more than capture compare register 0, but the closer you move this up on this chart, the higher value in CCR1, the farther you're going to extend this pulse width here. So to increase the pulse width, you increase capture compare register 1 towards capture compare register 0. To decrease the pulse width, you just put a smaller and smaller number into capture compare register 1, and it's going to bring this pulse width in. It's going to basically reset the signal down here on the graph, and you're going to have a smaller duty cycle. And so It's a little confusing sometimes to get the pulse width modulation working right, especially if you're not used to, if you're kind of new to the embedded world and timers, but it's not too bad. So just read through the data sheet. Here we initialize our capture compare register to 10, and CCR0 is 25,000, so our duty cycle is really small. And then after that we set our output pin 2.1 to an output, and this will be our pulse width modulation pin. So this is port 2 bit 1, or port 2 pin 1, P2.1. if you look on the schematics for the launch pad in the chip, that's going to be the pin that our PWM signal comes out of. And so that way this is all handled for us. We don't have to really mess with the timer A1 stuff. Our pulse width is going to automatically be output by hardware. It's not going to take up any of our CPU resources. Next we configure the UART, because this is how we communicate to the Python application. The first thing you want to do is hold the module in reset. We're using UCA 0, so you want to put it in reset to configure it, then take it out of reset when you're ready to run. So first thing we do is enable reset to hold the device, the module in reset. Then we set the UART, or the UCA 0 module, to UART mode. After that we set the UART to use submain clock SMCLK as the UART's main clock, so that's 1 megahertz. And then here BR0 and BR1, these come out of a table in the data sheet. And so the way you figure these out, this is how you get your baud rate. And we want a baud rate of 9600, and we have a clock frequency of 1 megahertz from our submain clock. So what we do is go to the data sheet, go to the USCI interface in UART mode, and find this big table of baud rate so we don't have to calculate it. This is a lot easier. And the first column is our clock frequency. That's the 1 megahertz submain clock, our baud rate clock. And so we've got 1 megahertz right here. We want a baud rate of 9600, so that says that our UCBR0 register needs to be 104 decimal. If you convert that to hex, you're going to get a value of, I think, 68. Yeah. So UCBR0 set to 68. And there's another setting in here, UCBRS0, I think, or UCBRSX. This one is actually a couple bits, and we're going to set that to 1. So if you look over here, UCBRS1, and this is just required by the data sheet to configure the correct baud rate. And we don't have any settings for UCA baud rate 1 register, so that's set to 0. So that's how we get our 9600 baud rate. And next we have to enable the pins for the UART. And this is a little tricky too. There's an important section of the device specific data sheet you need to be aware of to figure this out, or else it's really confusing, is the peripheral selection bits. And so since we're using the UART peripheral, we need a RX and TX pin. And if you look at those pins, they say what peripherals are on what pins, but it's kind of hard just looking at the part to figure out what peripheral is selected by these select pins. So what you do is you go look at data sheet and you go to port schematics, and so we look at port 1, we want to use RX and TX. So port 1.1 is UCA0 RX, so we need that. And if you look over here, you have the direction, selection 1, selection 2, and they tell you how to configure it to get that peripheral to control that pin. So we want the UART module to control the RX pin. And so the directions controlled by the USCI, so that means that when you configure the USCI in UART mode, it will deal with the direction. You don't have to set that, it'll set it for you. But you do have to set the select bits both to 1. So P1 select here and P1 select 2 here, both need to be set to 1 so that the UART will be able to use those pins as RX. So if we go back to enable pins P1 select and P1 select 2, we enable bit 1 for both of those. That allows us to receive serial data. And then if we go to P1.2, we've got TX. Same thing. We want to enable in these two columns bit 1 for P1 select and a bit for P1 select 2. And do that here as well. So we enable both pins since they're both set to 1s in P1 select, and we enable both bits in P1 select 2. So now our UART controls the pins as it should. We don't need to set this P1 direction actually. That's set by the module. And then now that it's configured, we can take it out of reset, which is what we're doing here. Use the AND equals operator and not, so that you can set one bit to 0 without affecting any of the other bits. That's this basic digital logic. And then last thing we do is enable the interrupts for both receive and transmit, and this is just a general interrupt for UCA 0 RX interrupt and UCA 0 TX interrupt. So that way when we receive or transmit anything, we'll throw an interrupt and go execute what we need to in our interrupt routine. The next thing is to set up the ADC10. This code you actually don't need. I'll probably remove that. The first thing we do is set up the input channel. This sets the channel to 1011, and if we look in the data sheet under the ADC10, we did this because I need to sample 2 channels, and I just decided to have it do a sequence of channels. So 1011, so we start here at VCC minus VSS over 2, and we're going to sample here, and you'll see in a minute we've got this in sequence mode, so it's going to start here and pull a sample from each of these channels, even though we're only using 2, and then start back here at VCC minus VSS over 2. And this is kind of a good thing to use because you get a good reliable value. It's basically VCC divided by 2, which is, you know, usually 3.3 or 3.5, and so you get a steady voltage to make sure your ADC is working correctly. So back to our code. Our input channel is set to that channel. We set our ADC clock source to submain again, so 1 megahertz. We set our conversion sequence mode to a sequence of channels, and as I just mentioned, that means that we're going to start sampling at this channel, and then it's going to decrement, sample that channel, decrement, sample that channel, all the way till it gets to channel 0, A0, and then we'll start back over. And that way the ADC will automatically sample those channels for us. We don't have to keep interrupting and having the CPU run instructions to step through each channel. Let's see, the ADC10 DIV sets the ADC clock divider to 1, so we're not dividing, it's running at a megahertz. ADC sample and hold time, we hold for 4 clock cycles. You can calculate this up in the data. They have a section on this where if you know your figure out your source impedance and all that, you can figure out how long you need to hold. I'm driving these analog outputs with op amps, so I don't have a lot of source impedance, so I really don't need to sample that long. Here, see, here's the equation. You've got your voltage, analog voltage you're sampling here, you've got your source impedance, and then this is the equivalent circuit in the MSP430. And so what you need to do is measure the charge on this cap, so you have to give it enough time to fill up. So to do that, you make sure your sample time is greater than your source impedance plus your input impedance times the natural log of 2/11 times the capacitance here, CI. And so long story short, use this and you can plug in your source impedance. Again, mine was not much. I'm driving this with a unity gain buffer, so I'm not really too worried about it. And for their example, 10k ohm, their sample time was 2.47 microseconds. And so if you calculate up, you know, the sample time for me, I think it's somewhere around 4 microseconds because of the required sample time. But that's where you figure that out. So 4 works pretty well for me, and it's quick, so I stuck with that. So that was our, let's see, that was our sample and hold time. Next is our enable interrupt, ADC interrupts, because we want it to interrupt every time it's done running through these channels. We also want to enable multiple sample and conversions. Since we're in sequence of channel mode, we want to enable it to sample and convert multiple samples. We turn our ADC module on. One key here is that I'm using an external voltage reference, and so we have to enable that. This selects our reference voltage range to be VE ref for V plus and VSS for V minus. So V plus and V minus are going to be the range of voltages you can sample through. So if you set it to VCC, V plus will be 3.3 or whatever your VCC voltage is, and VSS will be ground. For me, I wanted to use ground, but I wanted to sample at a lower voltage so that my samples in voltage in millivolts matched up for easier division, as we'll see later. So I set my own custom external reference voltage, I think to 2 volts, to make a lot of my math easier further into the program. And to do that, it's a little bit tricky, but the key here is the block diagram in the data sheet. If you read that, it points it out pretty well. Let's see. What I ended up using was the external reference, and where is that? There's an internal one too that you need to look out for, because the internal one only provides 1.5 and 2.5 here if you turn reference on, but what I wanted to use was this external channel, which was VR plus is VE ref, which is external reference voltage. And if you use the external reference voltage, I'm trying to remember where it was. Oh, here it is, VE ref, right here. And so what you want to do is, this is where your external reference voltage goes, and that's going to be connected to an external pin. And to use that, you need to set this multiplexer right here with your S reference at 0 and S ref 1 to pass through to VR plus in the ADC module this VE ref, which is going to be 1, 0. So if we look back on our code, let's see, VE ref, S reference, we set it to 2. So that's going to set the 2 bits to a digital binary 2, which is going to be a 1, 0, which is going to be this. So it's a little bit confusing, especially if you're kind of new to this. You want to set these bits such that it uses this V external reference plus, and you pass that into the ADC by using this multiplex right here. And so that's kind of how you figured out these 2 bits are the control bits for this MUX. And if they're set to 1, 0, then you pass through VE ref. If they're set to 0, 0, you pass through AVCC. If they're set to 0, 1 or 1, 1, you pass through this internal 1.5 or 2.5 voltage reference. So be careful there. If you don't use VE ref, you'll be stuck with a 1.5 volts or 2 volts, so don't let that trip you up. You know, if you're confused, check that out in a little more detail. And then we set our analog bits. ADC10 AE is the register you use to set which A0 or A7 or whatever. We're using A5 and A7. So here we set the pins that associate with A5 and A7. We tell the ADC that those are going to be our analog inputs. So that way it knows to enable those pins in analog mode, and we're able to sample them correctly. And let's see. The last couple things we do is we enable the data transfer controller. And in the ADC, there's a data transfer controller, which is pretty great. What you do is basically enable this thing, give it the address of an array, and set up sequence of channels. And as it samples each channel, this data transfer controller will automatically store that sample value in that memory space of that array, and then increment, and then it'll sample the next channel, and since it incremented its little pointer, it'll store the next sample in the next array value, and then it'll go to the next ADC channel, get that sample, store that in the next array, and it does that until it's out. So for example, what we do is we have 12 channels. If you look back at the data for ADC10, we start here at basically VCC over 2. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we need a 12-byte array. So this ADC is going to finish this sample, and then instead of throwing an interrupt, it's going to tell the DTC that it's done, and the DTC is going to store this value in the first byte of our array, and then it's going to go to sample the next analog channel, and then when it's done, it's going to tell the DTC to store that byte in the next value of our array, and it's going to do this till it gets to the last value in our array. It's going to store the last sample value, and then after all that's done, we're going to get one interrupt request that says all of your data is done and it's been stored in this array. I'm finished. And so that's great, because instead of interrupting after every channel or interrupting to store each channel, it's going to do all the channels and store them for us, and then at the very end it'll throw one interrupt for this entire process. And so that really is a big help, because it frees up our CPU to do a lot of other things. And just a quick check of the DTC block diagram. There's a lot of information here. I'd recommend you read it. But let's see. We're using one block transfer mode. We won't get into that. And we want the repeated channels, so I think that's this one. So you start the DTC, initialize it, and it waits, and basically runs through this and stays in this transfer mode till it's transferred all the data that you tell it. You tell it how many bytes it's going to transfer, and what happens is when the ADC is going to throw an interrupt because it finished a single channel, instead it tells the DTC, and the DTC comes down here, stores it, increments your pointer, and then waits for comes back up here to idle and waits for the ADC to tell it to write another value. And so that's a lot more efficient than us doing it with the CPU and interrupting constantly. So that handles all of our data transfer for us, which is pretty convenient. So the let's see, the last thing, where is this? The last thing that we do to configure this data controller, we want to tell it 12 bytes in DTC1. That's the register that you write the total number of bytes that you're going to be transferring in one sequence. Remember, ours is going to be 12. Then you give it a start address. So this ADC array that was up at the top here is our array that's going to hold all of our ADC samples. And we're going to have 12 total samples, so we need 12 members in our array. And it's a little confusing because you have to do some typecasting. What's going on here is you take ADC 0 and you take the starting address, memory address of ADC 0, and then you convert that to an integer just so the compiler knows that you're purposely storing a pointer as an integer in this register. So if you're not familiar with this, you need to look at pointers, and maybe I can make something about that in the future. But you basically just take this pointer, and because it's a pointer and not an integer from the compiler's point of view, you need to explicitly tell the compiler you're storing it, pointer, in a register that really expects an integer on purpose. So you do that by typecasting, and so all you do is put the type in parentheses in front of the pointer, and now the compiler knows that this pointer is supposed to be an integer and it's okay to store it in this register. And so that's pretty much it for the configuration of the ADC. The last thing we do is enable it and tell it to start conversion. And in the datasheet it says you can do these both at the same time. That's why I did it. And I just copy and paste it. So you may see this line over and over again. But so now we can start conversion. And the last thing we do is enable global interrupts here. And our system's up and running and ready to go. So let's jump down to some simple interrupts real quick, so this video is not too long, and then we'll make a second part to discuss some more complicated ones. The first one is the interrupt for timer A0, as we mentioned above, and it's going to be for capture compare 1 and 2. If you look at that, you've got a timer A interrupt vector table, and so that's pretty handy. What you can do is a switch statement to switch on that, and then just make a case for each capture compare register. So if we look in the data sheet at timer A and go down to the registers and find the register that is TAIV, here's the table. So when you get an interrupt, there's going to be a value in this table, and it's going to be your interrupt flag that says an interrupt is pending. So 02 is going to be capture compare register 1, and 04 is going to be capture compare register 2. So if you interrupt, you want to check this table, which is a 16-bit register, and it's this portion, and so you can use TAIV because it's in the header file. And if TAIV holds 02, then your capture compare module that threw the interrupt is CCR1. If your TAIV table holds a 4, then CCR2 threw the interrupt. And we're not using overflow, but if the timer was to overflow, you could also interrupt on the overflow, the FFFF, if it threw a 10. So what that equates to in code is we'll switch on TAIV, and every time we interrupt, we'll execute this switch statement, and we'll have one case for CCR1, which is value 02, and since we interrupt twice a second and we want to send our plot data once a second, we'll put one count in here, so we'll send our plot data every other interrupt. So that gives us our 1 second frequency or update rate. And so we enable send temperature. This is a blocking flag, and you'll see because we send our updates a lot faster, I wanted to make sure that if we send a temperature byte to plot, it doesn't get interrupted or messed up or just not sent because we're already doing something else. I don't want them to create a problem with one another. And so I put this blocking flag in there, send temp, that says I'm currently sending a data packet to the GUI for plotting a temperature, and this basically takes priority. It basically, this other update temp for our, down here, case 4 for CCR2, it can only execute its code if I'm not sending a plot byte. So I write a 1, and on the GUI side you'll see that's a header that denotes that we're sending a graph plot, a plot byte for our graph. And so we send that one. Since we enabled transmit interrupts from our UART, we send a 1. When that completes, our TX interrupt vector down here is gonna throw an interrupt flag, and we're gonna come and execute. And the first thing we're gonna do is send temp as a 1. If it was a send data plot, well, actually these are the same. So really, we're gonna check our interrupt flag and clear it down here at the bottom as usual. And then if send temp is a 1, which it is because we're sending temperature, we're going to go through these if statements, and if you don't understand how these work, it's pretty simple. You're going to interrupt every time you complete sending, or every time you complete sending a byte over the UART. So we sent a 1, our header byte, and when that's done, we're going to interrupt, and this interrupt routine is going to see that we're sending temperature because that's a 1. So then it's got a counter to see what byte we're on, and it's going to say, okay, the next byte that we're going to send is average temperature, increment our counter, and then from here we're going to exit our interrupt routine. And when that byte, the average temperature byte, completes sending, then we're going to interrupt. We're not going to execute this because our counter is 1, so we're going to come down here, see that our counter is 1, send our room temperature byte 1, and increment our counter, and then go to the end of the interrupt and exit. And then we're going to send the last byte when the room temp 1 byte completes, and we interrupt again. We're going to go down here to send room temperature 2, clear our temp count, and leave. And we're going to clear our send temperature flag. And the same thing is going to happen over here for our update temperature flag as well. So they're the same thing. I actually copy and pasted these two. I wrote 2 down just because it's a little easier to see than switching you having two things send the same stuff out of the same little code block. So hopefully this makes a little more sense than if I did it the other way. But they're the same, and so that's how that works. And our CCR2, as I said, we're gonna, oh well, before we leave, we're gonna clear our count if we sent all this data, and then we're gonna append another count displacement to our timer, because remember, we're counting up to 62,500. So when we get to 62,500, we don't want to clear it and then count up to another 62,500. We just want to keep going, because this thing will just keep adding and adding and adding, and our time will be off. So you want to append, because you want it to interrupt every 62,500 cycles of the timer A0 clock. And then the last thing we do is clear our interrupt flag and break. So this is how we handle our capture compare register interrupt. This main state seconds is a counter to count seconds, because we use seconds to figure out our hold time in our main state machine up in our main while loop, but we'll go over that later. Case 4 is CCR2. It's kind of the same idea. We check to make sure we're not sending a temperature value to be plotted. If we're not, we set our send update flag to 1 to denote we're sending an update to the interrupt service routine for the TX vector, and then we send our data byte. 2 tells the GUI that we're sending an update packet to update its room temp and thermocouple temp on the main program. So this is not a plottable figure. This is just to update. And so we send a 2, we enable our send update. When we complete sending a 2, our TX interrupt vector is gonna be serviced, and in here we're gonna come in, check our flag, and we're gonna see that send update is set to a 1. That's the flag that we just talked about. And we're going to do the same thing. We're going to send 1 byte, then when that completes, we're going to send the next byte, then when that completes, we're going to send the next byte, clear our flag, and clear our counter. And every time clear our interrupt routine. So that's capture compare register 1 and 2. That's how our comm links work. And we'll go over the rest of the functionality in the next video.